All right. Hello, everybody. Thank you for coming to this Expo workshop on graph neural networks and TensorFlow, a practical guide. I'm Brian Prosey, the lead of the GNN team. And what I'm going to talk to you about before we start talking about, maybe more nuts and bolts stuff is like a high level, like what the GNN team at Google is and the kinds of research we've been working on in the last year. After that, we're going to talk a little bit about what is a graph neural network and the kinds of things, if you have no familiarity with them, the kinds of problems they can solve. And if you do have some familiarity with them, then right after that, we're going to talk about the things that TensorFlow GNN has been designed to make easy, like to deploy new graph neural networks to different problems around Google, because that's kind of how our team functions. So what does our team do? So we do research on how to apply structure to neural network models. We build a library to deploy these models internally, which we open sourced. And so we do a lot of infra and training for deploying GNNs on Google systems. And we do a lot of custom modeling applications. That's kind of the part I like. So we try to build graph neural network models that make Google systems better. So one of the challenges that we've been dealing with for a long time is that big graphs are complex. So the data sets that we work with are some of the largest in the world, I assume, and they frequently don't match the characteristics of the kinds of data that you see people use in academia. And this is going to be kind of like a reoccurring theme. I'll probably have a couple slides about this. And so one way that data is different from what you expect is that, or from what you might expect from like what you see in academia, is that there's a lot more kind of variance, a lot more like different modes of connection that can happen in your graph data sets. And so early on, we started working on graph neural network models that could do better in the presence of data that didn't exhibit high homophily. And homophily is when there's edges that connect nodes that have the same label together. And so we noticed that the data sets we were trying this on, it didn't work, and then we tried to figure out how to make that kind of model better. So we had a fairly popular paper at ICML a couple years back on this topic. Along the lines of trying to understand how GNNs work on more varied data sets, we've had efforts on benchmarking graph neural networks. So we had this kind of series of work called Graph World, where what we try to do is simulate like a universe of all possible graphs and all possible different kinds of connection types, and then train millions of graph neural network models so that we can get like the response surface of them with respect to graph properties. So that was at KDD last year. We have some upcoming work where we added new graph generators, and we looked at at a workshop on graph learning and benchmarking. We'll be talking about that. The paper's on archive if you're interested. Along the same line, another challenge we have is that if you want to benchmark a GNN on the data set, you might not actually have access to the data, because the data could belong to somebody else, or there could be some kind of privacy concerns. So we investigated private benchmarking of GNNs. Basically, can we learn a graph generator that generates graphs that are close enough to some ground truth data set, but they don't actually have any identifying information in them. So this is a paper that we'll be presenting at this conference, I think on Wednesday. Don't hold me to it, I have it written down on the slide later. But it's on, so we learn graph generators that can generate little subgraphs that appear like they were sampled from some larger graph, because we're always dealing with kind of big data sets. And I think it's a really interesting line of work that there hasn't been a lot on, so you may be interested in this if you're interested in the kind of this area. Another challenge that we've been working on this year is how do we know when unsupervised learning works? This sounds really silly, but what happens in practice in industry is that what people will do is they will run an unsupervised learning algorithm, and then they'll do some further experimentation to figure out whether it works or not. But that can be like a really long process. We would like to know ahead of time if our unsupervised learning worked, or whether it returned a trivial solution, or if it's better than random, right? There's all these different criteria that we could use to try and figure out when unsupervised learning works in kind of an unsupervised way. And so we examined some linear algebra methods that seem to correlate pretty well with task performance in this paper. It'll be in the Tag ML workshop on Friday. Another thing that we're talking about at the conference is our work on graph learning, and This matters a lot because we deal with a lot of data sets that don't have naturally occurring graph data sometimes, so we have to kind of extract the right kind of graph edges from the information. So we have a kind of like a meta model for, we call it graph structure learning, and we're going to talk about this meta model for graph structure learning at the TagML workshop again, and probably at other points throughout the summer. So if you're interested in graph structure learning, please check it out. The paper should be available. And then one more, this is at UAI, it's not at ICML, but sort of when you sample, you're implicitly kind of choosing a graph to operate over, so kind of like the graph design that I just talked about. By changing your sampling strategy, you're kind of effectively choosing the mode of propagation for your data. And some work on sort of learning a sample function. It's kind of the same as learning a graph, but you're learning it through sampling functions to like maximize the performance. So we have this thing called submix that's at UAI, and that paper is also on arXiv. For any of these papers, I know I'm going through them real quickly, but if they pique your interest, please talk to us about them later. Any of these people can talk about them. And I guess my boss requires me to put this slide in every presentation. So the Graph Neural Network group is a part of the graph mining team in Google Research, who focuses on more than just graph neural networks. We look at scalable algorithms for sparse data. That could be things like clustering, link prediction, balanced partitioning, all sorts of interesting sort of resource assignment issues as well. And we power hundreds of projects. The team, the parent team and its child team. We power hundreds of projects at Google in pretty much every product that you've heard of, because sparsity is everywhere. If you're interested in more information about the graph mining team and the things that we do, we had a NeurIPS Expo workshop just focused on the graph mining team. It's 3 hours of recorded presentations that you can just find online and watch them on YouTube. And if you like clustering, there's clustering talks. If you like distributed graph algorithms, there's talks on that too. Of course, we've done more since then, but that's the most comprehensive public description of what we do. All right, this slide is everything. I'm just going to go through this real quick, just everything I said. So we have the tutorial today. We have a talk on large-scale graph embedding, a paper I didn't mention, but it's very exciting, at the Google booth on Tuesday. And then on Wednesday, we have the paper in the poster session. And then Friday and Saturday, we have stuff at the workshops. And so, yeah, I guess I'm going to go to my fellow presenters, in order, Jonathan Halcrow, Brandon Meyer, and Anton Tsitsulin. So Jonathan, please take it away.
Thank you, Brian. Hey everybody, I'm Jonathan Halcrow, and today I've got the easy part. I'm going to tell you 3 things. I'm going to tell you very briefly, what graph neural networks are. Then I'm going to tell you some things that you can do with them, and I'm going to tell you at a very high level what TFGNN actually is. Before I tell you what any of that stuff is, first I'll tell you what a graph is. So a graph is, this thing over here. We've got some nodes, we've got some edges connecting them. Importantly, we're going to sort of consider graphs where we have different types of nodes maybe, and also maybe different types of edges. So as an example, we'll just for some of these next slides, just think about like an online social network. So we've got nodes maybe corresponding to users. We've got maybe nodes corresponding to posts, and then you have edges maybe corresponding to like friendship relationships or engagement with posts, things like that. And then importantly, we're also going to consider a type of network where the nodes also have some sort of features associated with them. So in our social network, our users might have ages, cities, languages, things like that. And then the real question that we're here to tell you about today is, how do we do machine learning on these objects? And so before I tell you about how we do that, I'll start with an analogy to convolutional neural networks. So in a convolutional neural network, we're normally given images as our normal sort of input, and the image, the convolutional neural network, will have some filter that will pass over the image, doing some matrix multiplication. And that'll produce a representation of the image that then we can use for different tasks. Like, we can do a classifier to say, this is a dog picture. We can do captioning, say, oh, this is a golden retriever on a leash walking in the snow. And we can even do stuff like segmentation. So we have like a background and some snow on the ground, and then we have our dog in the middle. And so all of those tasks are enabled by having this convolutional neural network. So what are GNNs? Well, maybe unsurprisingly, GNNs are neural networks on graph structured data. So similarly, we're going to have a graph as our input modality. And then instead of the convolutional filter, we're going to try and generalize that. So you can think of the convolutional filter as doing message passing between pixels through this matrix multiplication operation we're doing. We're going to do the same thing, but we're going to sort of break this up so we can do arbitrary connections between sort of arbitrarily structured nodes. And then we combine these representations per node, say. And we can use that to classify the individual nodes. So maybe we can say, oh, node 0 here is someone that likes basketball. We can do link prediction. So we can take this graph and say, oh, there should be an edge here between node 0 and 1. Or we can do things like whole graph classification. So say our graph corresponded to like the execution graph of some sort of application. And we can say, oh yeah, this program contains malware, something like that. So, okay, so now node classification. What does that look like? So we're going back to our social network. Maybe we have some labels corresponding to user interests. And then we have a bunch of unlabeled nodes. And then we want to try and predict labels for the unlabeled ones. So GNN is perfect for that. So we'll do message passing on the network. So this node in the center will receive messages from its neighbors. We'll combine them in some way and maybe iterate this a couple of times. So we're drawing messages from further out in the graph. And then we combine that representation to make a prediction for the user. That version of it, we're doing single hops. We have other versions of this where maybe you can do information from multiple hops at one time. So you can see our mix hop paper a couple of years ago. For link prediction, same kind of thing. We have our social network, and where we want to try and make a prediction using these representations about whether or not there should be an edge there. So a quick aside. This is a subject that's sort of near and dear to my heart, which is, where do these edges come from? In industrial settings, sometimes you don't really have a graph, or maybe we have many graphs. So we have a tool called Grail that we published a few years ago at KDD that does this task exactly. So we take some, observed relationships and some ground truth. We fit a pairwise model, and then we can use that for any sort of graph mining application. So in our paper from KDD, we talk about how we did this for YouTube, and from that you can see a lot of kind of interesting like subgraphs from this. So you can see abusive behavior corresponding to sort of dense cliques. You can see non-abusive areas of the graph, which are sort of sparsely connected. And you can see kind of interesting mixtures of those things. So if you want to hear more about that, you can see our paper from KDD. And then finally, graph classification. So a very common use case for this is for doing molecular property prediction. So in this case, our graph corresponds to some molecular structure. We apply some graph neural network, message passing neural network in the case of this paper by Gilmer in 2017. And then from this we can do things like predict will this molecule bond with something else, things like that. So the idea I want you to take away from this is that graphs are very general data structures, and so the tasks that you can solve with a GNN are likewise very general. So now I'll kind of go through a couple of applications. So, for a given graph, what are the things that we can do with it? So, we talked about social networks. We have users and comments. We can do node classification to predict users' interests. We can do link prediction to do friend suggestion, things like that. If you have a graph of, say, drug-drug interactions where the the nodes are drugs, and the edges correspond to some interactions. Like, you shouldn't take these two drugs together because something bad will happen. You can do node classification on this graph to try and predict different properties of the drugs. Link prediction might be really useful on this, so you can try and predict new interactions that you don't already know about. Another common type of application would be for like recommendation systems. So you might imagine you have some kind of a bipartite graph where we have users and then videos from say your favorite video sharing service, and we have some data about these users with these features have watched these videos. Maybe we have some embeddings for the videos as well. We can use that structure to help improve a video classifier. So maybe we can tell both from the video features, but also from the audience that's watching the video, what the video might be about. And then similarly, you could use link prediction on this graph to try and identify new videos that you want to recommend to users. Another very common application, at least in the literature, is for citation networks. So you have a citation network where you have articles, and then they're linked to other articles that they cite. You can do node classification on this to predict, what is this article about, based on the, maybe some text from the article plus what it cites. Or you can do link prediction to try and say, what are some other related works that maybe aren't directly cited by this paper. And there's a ton more applications. This is sort of just a very brief survey. You can do all kinds of kind of classic graph applications, like finding shortest paths. You can solve combinatorial problems, like solving interlinear programs. You can model physical dynamical systems, and yeah, the list is sort of unending. So that takes me to the last point. What is TFGNN? TFGNN is the thing that will let you do all of this. You can think of TFGNN as sort of having a couple of different layers. So it's our Python framework built on top of Keras and TensorFlow for training graph neural networks. So at the base layer, we have our sort of data representation layer for doing things like reading and sampling graphs and representing them in TensorFlow, importantly. We have lower level operations for doing, say, message passing on the graphs. And then we have some higher level APIs for practitioners, where you can implement your graph neural network in a few lines of Keras, which Brandon will tell you about in a minute. And we also have an orchestrator, which will let you sort of run all of this together with sort of minimal amount of code. And with that, I will pass it on to Brandon to tell you more about TFGNN.
Hello, my name is Brandon Mayer. I'm a SWE at Google, and I work on problems in graph learning and GNNs. I'm really excited to be here at ICML to get a chance to talk a bit about TFGNN, which is an awesome machine learning framework for graph neural networks. So I'll start by going over some of the primitive objects in TFGNN, how they work together to develop graph learning pipelines. I'll introduce some of the fundamental TFGNN data structures, which are called graph tensors. I'll walk through some examples of what a simple GNN looks like using TFGNN's low-code solution we call the runner. And at the end of this, you probably should be able to run your own custom models using TFGNN on standard data sets. So this slide visualizes what a typical TFGNN graph learning pipeline looks like. The pipeline typically starts with some graph data. It's on disk or held in a database or in memory on one or more machines. And for most problems, like node classification that Jonathan was talking about, or let's say link prediction, a modeler might want to generate sampled subgraphs from a much larger graph and format the subgraph in a data structure that TensorFlow GNN can understand. In TFGNN, graph data is represented, as I said, by this graph tensor object, and it's the fundamental primitive object of the framework. Simply put, a graph tensor is an extension of the normal tensor object you'd find in any other ML system. Thus, the output of the dataset providers in TFGNN, which we'll also go over, is a graph tensor. And GNN models are defined as functions mapping from graph tensors to graph tensors that modify some sort of hidden state through message passing or other GNN functions. So TFGNN has a lot of low-code solutions to get you up and running quickly with GNNs on standard data sets. To start, TFGNN comes bundled with some what we call dataset providers. It's a module that can download and prepare standard GNN datasets into formats that TFGNN can handle seamlessly without a bunch of custom user code. This is especially useful when you start to develop your own GNN model and you want to quickly establish a baseline against, let's say, some standard benchmarks. For example, a user can work on standard OGB datasets or Planetoid or Network X or many others right out of the box without worrying about writing custom I/O. The framework also provides, as Jonathan was saying, this runner orchestration module that handles all the boilerplate code to run training, validation, and inference on multiple hardware setups. The runner leverages a lot of the TensorFlow APIs and abstractions like TF Data Service, the distribute APIs to instantiate these pipelines on either a single machine, a whole cluster of machines, or using accelerators such as GPUs or TPUs with minimal code changes. If you wanted to do this from scratch, there's a lot of hoops you have to jump through on your own, but the runner framework makes that very easy. And when you're using the runner orchestration layer, you as the user would provide some implementation, some key abstraction that the pipeline defines, such as maybe some data preprocessing functions, the actual GNN model, and a particular task like node prediction, node classification or link prediction. And we'll touch on each of those pieces as I go along. But before we dive into the actual pipelines, let's look at some graph data and the fundamental object that TFGNN uses that I've been talking about, the graph tensor. To take a look at the graph tensor, we could experiment with TFGNN's data providers. Here we're loading the OGBN mag node classification data set that's standard in the GNN literature. And if you're unfamiliar with this data set, it's a citation network like Jonathan was talking about, and has node types like papers, authors, institutions, fields of study, and edge sets, which are relationships between those node sets like rights, affiliated with, and sites, and so on. And while the original data defines one large heterogeneous graph, the dataset provider by default will define the transformations on this original data set to generate random subgraphs from this large graph. And this subgraph, finally, is what is represented as a TFGNN graph tensor. And this tensor object is just an extension of normal tensors like you'd find in TensorFlow. So we could use this data as an example to look at what a conceptual layout of a graph tensor might be. Again, it's just a composition of other tensors with potentially different shapes that encapsulates those objects that we want to work with, nodes, their associated data, and the edges that connect them. And in TFGNN, the heterogeneous graphs are a first-class citizen, meaning their support for multiple node and edge types are built right in. This is an example of what a graph tensor from the OGBN MAD could look like. And the graph tensor itself has a few named properties like node sets, edge sets, and they're keyed by the name of each graph piece. And we'll look at some code in a little bit to make this visualization a bit more concrete. So in this example, the graph tensor is holding three node types, the author type, a paper type, and a field of study. TFGNN has a reserved field hashtag ID, which tracks the original identity of the node. And typically in TFGNN, anything starting with the hashtag symbol is reserved or special under the TFGNN framework. The authors, the fields of study nodes, don't provide any features, but the papers come with a bunch of features like an embedding vector over the content of the abstract, and maybe like the year of the paper was published. Edge sets are the typed relationships, each with their own name, that define edges between the node sets, and it's indexed according to the order of their node set list. So, for example, let's say the rights edge set, which was the relationships between the authors and the papers that they wrote, you can see that outlined here. Every edge set will have like a source and a target key, which will enumerate the relationships between the source and target node sets. And the edge sets can define relationships to and from the same node set, like the sites edge set. It relates papers back onto the original node set papers for papers that explicitly refer to other papers. And to make this more concrete, we can print out some values from the original code example in a few slides before this. We could try this out in a Google Colab very easily with just the subgraph that you instantiate would be a little different from this example. And what we can see here is that in this subgraph there were 41 paper nodes sampled, and we were looking at the node features named feet, which is the embedded paper abstract. The embedding vector in this data set is 128 dimensions, and when indexing into the graph tensor paper feature, we get an entry or a matrix with the expected shape of 41 by 128, which is the 128 vector for each of the 41 papers. And then for completeness, we could look at the same graph tensor's edge lists. So for this example, we're just looking at the right edge list. It has adjacency information, establishing relationships between the source, which is the authors, and the targets, which are the paper nodes. And if we print out the adjacency, source, and target properties, we can see they're just shape-aligned, normal TensorFlow tensors enumerating the 16 rights edges found in this subgraph. So far, we focused on how to generate sampled graph tensors using standard data sets. You can try out a different data set by changing a single string in a Google Colab and using TFGNN's data set providers. And we spoke about how the graph tensor object holds this graph information in a very simple, intuitive, nested structure of named tensors. Next, we'll focus how to build a GNN and inject our model into the GNN orchestration framework, which we call the runner. From Jonathan's slide, if you can recall that the runner is just a term for an entry point into the TFGNN library that orchestrates training, validation, and testing using user-defined objects. This runner orchestrator does all the heavy lifting to be able to run your GNN pipeline in a variety of compute environments. Again, it's useful to make this more concrete just by looking at a simple code example. In this context, the runner framework is just a module that we can import, and it provides like a main entry point or a function. And here you can see the runner.run function that we'll call to complete training over a task. We'll walk through the steps used to inject the necessary functionality to run node classification on the OGBN mag dataset. And while we're looking to run node classification in this particular example, the code and structure is very similar if you were doing something like link prediction or graph level prediction or regression. The train provider is just the same OGBN mag dataset provider we created a few slides back and we're already working with. This is the thing that creates graph tensors that will feed into our pipeline. Next is this model FN function. So this is a user-defined function that we have the expectation of returning a Keras model. This is where you as the user would inject your GNN model code, and we'll look at a simple example pretty soon. The runner knows a lot about common GNN tasks like link prediction and node classification. Using the baked-in TFGNN dataset providers, the tasks are already configured along with the dataset, and we can pass the particular task into the runner in a format that the runner already knows about just by referencing the task on the dataset. And then finally, the runner allows us to apply some optional pre-processing functions to the input prior to pushing graph tensors to the trainable model. And I'll go over that in a little bit. So again, before we get to modeling, one of the key transformations we can perform on our input data through the runner API is feature pre-processing. So this is a chance for users to define a set of transformations that are applied to the graph tensors that are produced by the underlying dataset provider. So this dataset provider is just giving you some graph tensors, and you can provide whatever transformations that you want to on this graph tensor before they get pushed into the training pipeline. In this example, the user is defining a function named process node features that conforms to like the expected API signature and performs different functions for each of the node sets that are defined by the OGBN mag example. And we're just simply hashing some ID fields like the field of study or the institution. For the authors, the user returns an empty feature indicating there are no features associated with that node type, and we'll just be using it for its topological connections within the model. And the pre-processing function is added to a list of feature preprocessors that the runner API expects and is called on each of the graph tensors that the dataset provider generates. There's one key step before we can go on to modeling, and that is initializing the hidden states of our graph tensor. Again, we focus on transformations applied to node sets, but this you could have edge set features or graph level features. There's very similar injection points in TFGNN. Here we're mapping the hashed field of study to a 32-dimensional learnable embedding vector, and we're doing the same thing with the institution ID. We extract the paper's embedding features and we pass it through a dense layer. We're producing a 512-dimensional representation of the original embedding feature in this particular example. It could be anything that you want to do. And while the structure of this function and its signature looks very similar to the pre-processing step, there is a key difference. The feature pre-processing doesn't define any learnable variables. Instead, it's just a way that we can inject some pre-processing functions into the runner API. But this initial hidden states injection point allows us to define transformations that involve learnable variables that will be updated during training. So finally, TFGNN comes with models, this models module that contains a lot of really good GNN layers, and you can stack them to create your own GNN model. Here, we're just using this vanilla MPNN graph update layer. There's a whole bunch of them, and we can stack them using the TF Keras sequential API. You could use any Keras API that you want, but the framework is very flexible. Here we're defining a model FN that we're going to pass to the runner. This model FN takes this graph tensor spec object, which we don't really need to know anything about at this layer because we're using our dataset providers, so we can just satisfy the runner API and think of the graph tensor spec as some sort of symbol. And so if you followed all of that up to this point, you should be able to open up like a public Google Colab and get to the point where you can run training and validation on any standard benchmark data set. You didn't have to define a custom loss or custom metrics. The runner is able to provide sensible defaults for these given the task, and it's easy to inject those into the runner, and you can check out the documentation for the runner API for further customization. We didn't have much time in this tutorial, but it should have given you enough information to understand how a graph is represented in Tensorflow GNN, that the Tensorflow GNN comes with off-the-shelf data providers that makes initial model development easy. And there's this runner orchestration framework that abstracts away the details of your compute environments, creating portable pipelines that work well with data providers framework. So we use the minimal code approach and let TFGNN do a lot of the heavy lifting for us. Normally, if you started from scratch, there would be a lot to make a truly portable machine learning pipeline. There's more details to know about the framework as you move down the stack away from the runner, but the additional complexity might be worth it depending on the type of problem you're trying to solve. In most cases, though, there's a lot of power at the runner orchestration layer, and we end up having a lot of impact at Google building our GNN models with the runner framework at Google. Thank you all for coming, and I hope this was a helpful introduction to TFGNN.
All right. My name is Anton. I will talk about running TFGNN at scale and all the fun things that you can do, and also present zero code so no one understands a thing. I will talk about, in general, large-scale sampling. So, like Google has large graphs, as mentioned before, and the approaches to sampling also differ a bit. I will briefly mention orchestration yet again, which is an integrated platform really good for all the industrial folks. Hopefully there are some. And I will also talk about TPU training, which is kind of a really good feature of TensorFlow GNN, and also mention some of the goodies that we've got for you. There are like 3 different approaches for large-scale graph training. One is you can compress the graph on the left, try to fit it on a single machine. If it doesn't fit on a single machine, buy a bigger machine on Google Cloud and try to fit it yet again. And you can rinse and repeat There are like 24 terabyte RAM machines nowadays. They're expensive, but they still cannot fit the largest graphs you can possibly think about. And they cannot fit large enough graphs that we work day to day in our group. So then there is graph partitioning, and well, we have some of the best graph partitioning people in the world, but it's still really hard to partition like complex heterogeneous graphs without losing much quality. So what we really rely on is distributed sampling, and this is open source. Apache Beam is kind of a orchestrator, and you can think about it as kind of a second generation of MapReduce, really. And this all runs on cloud with Dataflow and BigQuery. All you kind of need is just the definition of your graph data, and in terms of like its adjacency, node types, edge types, node features and edge features, and a sampling specification, which is basically telling in very much detail about, well, how are you going to sample from this node or that node, what is more important, how do you sample by weight, so on and so forth. And there is a brilliant Google Cloud blog post with more information, like a very in-depth example in the presentation, which will be made available on the QR code. So the runner is kind of the orchestrator tool, which we rely on a lot, because who has time to write 100 training loops in a year? It manages all the problems and interesting things about data reading, feature preprocessing, batching, which I will talk about in more detail, training with different tasks, and TPU padding, and I will talk about that with more detail, and also manages checkpoints and restoring checkpoints of complex models, which is also not trivial. In terms of data readers, we're like good citizens of Tensorflow ecosystem. We offer TF data integration for processing and TF data service to kind of allow really commodity-sized machines to serve your training pipeline, so nothing is really bottlenecked on anything, both data nor model training, and it's all automatic and nice. In terms of batching, we have the solution that I don't think that is really common. We have the sampled subgraphs and kind of put them as connected components in a larger graph. This allows us to kind of save a lot in computation and also save up a lot in terms of information that we pack there, in terms of like basically the sizes of tensors. There are a bunch of predefined tasks. This was told about a lot, but I will briefly mention that we have node classification and regression as kind of pre-baked, predefined solutions. Regression on graphs is also kind of non-trivial, so there are like a bunch of different losses metrics specified for you, so you don't really have your graph neural network overfit to end out with the mean, as it usually does. Link prediction in a scalable way with sampled subgraphs is also not something that is very common in academic settings, so we have kind of approaches to do that at larger scale. Again, graph classification and regression, again, non-trivial to train neural networks for regression, so like, again, like a bunch of solutions there, but if you look at the code of these tasks, it's really kind of easy, and it's really building on top of one another. And my thing near and dear to my heart, unsupervised learning on graphs, is also kind of a very common thing that we have. It's also hard in terms, to do it really well, because in academia, when people do unsupervised learning, they will take ImageNet or something like this, throw out the labels, and say, oh, we have an unsupervised problem. When people in industry do unsupervised learning, there are no labels, and there is really no one, I can go and cry to give me labels. And if I had labels, I would do supervised learning instead. Like, why would I handicap myself for unsupervised learning? So there are a bunch of really use cases, and the whole framework of thinking about unsupervised learning is way different. So we also offer like a bunch of explainability stuff. So in this particular scenario, the node A in the middle is classified as a blue square, and well, we can kind of find out the path to it via integrated gradients, and the integrated gradients provide us with a per edge and per node explanations. Here I kind of plotted per edge explanations, but also like nodes are shaded in a slightly different way, and we can see that this node in the circle node in red is the most important node for this prediction. All right, here is one sidestep, and here is another plug for the TPU graphs. TPU graphs is a large-scale graph regression problem that aim is to improve TPU program optimization. So it's really a completely different domain from what people have been doing with graph, call graph tasks, and it has a particular scale that is not really seen before in academic benchmarks, at least on program things. There is a malnet for classifying graphs as malware that was available before, but I don't think that had features associated with the graphs. And we released this data set on GitHub. And hopefully we'll try to do some more interactive contest-like things in the future. And of course, by improving on this problem, you also make your life in the future easier, because if we know how to optimize things on TPU better, we can run things on TPU faster, which is of great help. Unsupervised learning is represented in terms of contrastive losses. So basically we have kind of our true graph on top, and we corrupt it somehow. It has been done a lot in image processing literature in this particular framework of thinking. We also follow that. And we have some kind of a contrastive operators. We have implemented state-of-the-art things from image folks there. And we also allow like very customizable heterogeneous corruptions that are not really present in any other library. Again, sidestep, and in this time, this is a self-promotional thing. We have, again, this problem that was mentioned. It's really hard to do modal selection for unsupervised models, because basically if you optimize for the, let's say, classification accuracy for the problem on this slide, then, well, it's very trivial to find a network that does that, but will this network actually learn good representations? Well, likely also no. The problem is really in balancing these things, and we have a bunch of evidence from vision folks that you can create unsupervised metrics that allow you to do modal selection and hyperparameter optimization, but these don't really work all that well for graph neural networks, nor for more shallow models. They're really, really specialized for this large-scale vision things. And we have a paper at TagML talking about all the different techniques we thought about to kind of alleviate this problem. And last but not least, TPUs. Let's talk for a moment about our Lord and Savior. Tensor processor units offer really good performance. Industry-leading speed and efficiency, also important. And also important, they cost less per performance on cloud. Don't quote me on that. They are also kind of great for training graph neural networks, although no one is really doing training graph neural networks on TPUs, because they all have to have this really annoying size constraints because TPUs are basically like ASICs. They require static shapes. It's really hard to get static shapes with graphs. So we have kind of a solution which is, I think, quite brilliant. It learns the padding, the bin packing problem on the fly from your actual sample data, optimizes the layout and minimizes the space for padding on the fly in the dataset provider without you doing any sophisticated optimization yourself. And this, for instance, reduces the training time in Colab. You can check it out in the repository today. On the public Colab GPU, I think the epoch of OGBN mag is like 30 minutes, and on TPU is like 90 seconds. And this is the TPU that you get in Google Cloud, which is not the latest generation. So you can see an in-depth collab later on with the detailed explanation and walkthrough on how to do that. And well, with that, thank you, or mahalo, on behalf of the TFGNN team. You can see the TFGNN paper link on the right, and you can also browse the GitHub and install right today. Thank you all. We do have time for questions. I think there are like microphones. I would assume that they're wired up on the right-hand side and on the left-hand side. Let's start with the fastest person. Great.
Fastest person. How big of a graph I can train on a single GPU? Just ballparking. Realistically, for a non-Google, so from outside of Google, you're just using Google Cloud, using multiple GPUs.
I think we have a public example of training a 10 to 100 million node graph on sampling on a public Google Cloud.
Did you say 10 to the 8?
No, I said 10 to 10 million, which is, I guess, 10 to the 8 node graph. But like in reality, the real cost is in sampling, because when you sample the graph, then you already have some small subgraphs that you feed into the training system. So it doesn't really matter as much for the actual accelerator rather than the pre-processing system that needs to scale.
Yeah, but say I have a data set which each graph is, say, 10 to the 7 or 10 to the 8. Is that feasible today? The data set itself.
Sure, yeah.
Each graph has, say, 10 to the 8, for instance.
Oh, okay. So you have a bunch of extremely large graphs, and
Exactly.
you want to do graph classification on them or something?
Or graph embeddings.
But embedding like each graph or each node?
Each node.
Okay, then please come to the booth demo on Tuesday, where we show exactly how to do extremely large graph embedding 10 to the power of 9 on TPUs on Google Cloud, I guess. Yeah.
Thank you.
I mean, can't we even get 10 to the power 10? Like, when will we stop at 9?
Yeah, I mean, like we don't really stop at 9, like Brian says. Like we can do larger, but like 11, 10, who knows?
Billions, let's just say billions.
Billions, yes, it's like billions with a B. So like a larger. So we have a person on the left.
Two questions, please. First, can you comment on the differences between this framework and DGL and 5G? And second, how easy it is to implement new GNN layers in your framework? If you have an example, that would be nice.
I don't think I can wire you up an example. I would suggest that you open up the GitHub and take a look at the implementation of the one of the, let's say, GCN or something like this. It's relatively easy. We do heterogeneous graphs first, so a simple GCN layer may seem more convoluted than it actually is, but it's kind of because GCN is not really suited for heterogeneous graphs. And things like transformer, heterogeneous transformers are actually much easier in the framework. The first question, Brian, do you want to? Yeah, I mean, it's.
Thank you for asking that totally unexpected question. So we do get it all the time. I think the obvious answer between us and PyTorch is, we're based in TensorFlow, not PyTorch. The answer between us and DGL is, it may be a little more complicated. So the two libraries kind of arose independently, and we have taken different strategies towards training large-scale GNNs, both from the kinds of accelerators we support to sort of the sampling paradigms. At this point, I think all three of them are fairly mature libraries. They have a lot of features. I have more experience with PyTorch than DGL though, so I can't speak as much to DGL versus TFGNN. I will say that we've been doing this for a long time, so it's our library is probably 6 years old, and the open source version is a little younger than that, but it's this is the third version I think we've done. Maybe so, yeah.
So it has a lot of things that work well for us. It may work well for other people, but I'm not a marketing guy. I'm a research scientist. So the only thing I can say is I'm not selling you anything.
Thanks.
Hi, yeah, great talk, thank you. Do you have like built-ins and strategies for tackling like temporally evolving graphs, or do you have any examples that that sort of thing?
Brian, take it now.
Do you want me to take that one?
Yeah.
Okay, yeah, great question. So we do have some. Let me think about this. So the way the framework is designed, there's like different ways that you could support temporally evolving graphs. Like you could think about supporting them in the training phase by like making sure that you sample temporally consistent data. I do think that the open source sampler right now isn't as I guess sample every two. Everybody's got sample every two, right? Yeah. So the new generation, the open source sampler, allows you to do things like using different features as part of the sampling process. You can create temporally consistent graphs for training your data. That was one headache that we ran into at some point. Other than that, I mean, it's very easy to couple and like to assemble time-aware models with your GNNs. So we have a lot of kind of fusion models that do like GNN for like graph processing, and then sequence information like rolled up into LSTMs and stuff like that. So it's like those kinds of like like in that sense, yes. In the sense that like, do we have a whole library devoted to like dynamic graphs? No. Although I guess that is an area we'd love to grow more in. I think. So like I think we have a lot of the primitives you need, but we don't have like an out-of-the-box package.
Okay, great, thank you.
Which also gives us to the point that Tensorflow GNN accepts contributions and has a really rigorous process for accepting them.
So do you think like we can use large language models or things like that to solve graph problems?
Oh man, this is a good one too. In some sense, let's say yes, but I guess I have a clarifying question. Do you mean use architectures like large language models, like cross-attention, or do you mean do you mean actually like just what's up?
Let's say use a GPT-4 and like fine-tune it or something.
Oh, sure, but the language model is the thing solving. You want the language model to solve the graph algorithm.
Yeah.
There's been I think a paper or two about this, like a graph-based data set for for this, like where they measure how well LLMs can do on like classic graph algorithms. They do have like a number of like, it's like a pretty big data set. Like maybe use like 30 different like different classic graph algorithms to see how well it did. So I think yes, but I think that's a very active area of research. So we'll know more in the future. But it's a good question for sure. Any other questions? We'll talk about anything, probably almost anything. If not, thank you for your time.
There is a question.
Oh, sorry.
So you mentioned about choosing some layers of neural networks when you build the GNNs. So how do you exactly select what would work best and what layer and so on?
That's a good question. The thing when we have labels, right? So life is easy with labels. So in that case, we're usually just doing hyperparameter search over many different possible architectures, and just like a standard, Vizier style search to figure out what the right architectures and performant architectures are. When we don't have labels, things are a lot harder because you want to be able to do the architecture search on the unsupervised stuff. And Anton?
Yeah, I mean, like we typically stick with whatever is tried and tested for unsupervised stuff and try to, because there's like a very limited hyperparameter tuning budget that you can expand because you don't have any good metrics. So you kind of want to keep the architecture probably out of that lately.
But that's also kind of motivated our research into developing better metrics for this, so that we actually can measure runtime, unsupervised learning, how well it's doing for use in things like search.
Thank you.
All right, well, if there's no more questions, we'll be around all week. Thank you very much for your time.